In this lecture, we will be looking more at curve sketching, but this time we'll be looking at the example of a rational function. And of course, the techniques we're using here are more general. You can use this for any function that's twice differentiable. These techniques are not specific to rational functions. One difference in moving from polynomials to more general functions, in addition to using the same steps that we use for graphing polynomials, we also need to deal with things like discontinuities. We need to investigate the behavior near those discontinuities. So think, are your continuities removable? Are they jumps? Are they gaps? Are they vertical asymptotes? And then we check the behavior at infinity, in which case, unlike polynomials, you may have horizontal asymptotes. So you may have a function that as x goes to infinity, you may be approaching a horizontal asymptote. So the first example of this that we'll look at is this function x squared over x squared minus 1. And the first thing we'll check is for this limiting behavior. So remember, when we take a function like this, a rational function, and we want to evaluate the limit as x goes to either positive or negative infinity, what we do is rewrite this function by dividing every term, top and bottom, by the dominant term in the denominator. And this allows us to more easily evaluate these limits. And so in this case, the limit as x goes to infinity of f of x is the limit as x goes to infinity of 1 over 1 minus 1 over x squared. And we learned in our section on limits of rational functions, we can use our limit laws to say this is the limit of the numerator over the limit of the denominator. And then the denominator, we use the difference law, which we often think of as directly evaluating this expression. And we make the claim that this term, as x is blowing up in size, 1 over x squared is getting really tiny and shrinking to 0. So this whole limit is 1. And we have the same thing as x goes to minus infinity. X is being squared, so the fact that x is large and negative doesn't change the result here. And so this is also equal to 1. And what this tells us is that f has a horizontal asymptote of the line y equals 1 as x goes to infinity and as x goes to minus infinity. This is very different than what we see with polynomials. Polynomials always take off to plus infinity or to minus infinity as x goes to infinity. Not the case with a more general function. We then check for discontinuities, and remember, with a function like this, what we're concerned about is when the denominator can be 0. Or x squared equals 1. So we have a problem at x equals minus 1 and x equals 1. And those will, in fact, be vertical asymptotes because we don't have a situation where we can factor the numerator and denominator and cancel something. So we'll explore that in a bit. But now let's get back into our standard approach. We follow those same steps, first order information and second order information. So we need the derivative. And so we can rewrite this as x squared times x squared minus 1 to the minus 1 and use product rule, or you can just take this as is and use quotient rule. Either one works. If we use quotient rule, we have denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. That can be simplified a bit. Multiply out the first term in the numerator, and we get 2x cubed minus 2x minus 2x cubed over quantity x squared minus 1 squared, and we see that the 2x cubed terms cancel. And we're left with just minus 2x over the quantity x squared minus 1 squared. This can only be 0, right? Remember critical points. F prime is 0 or F prime does not exist. And we see f prime equals 0, again, only if the numerator is 0. So that's the case where minus 2x equals 0 or x equals 0. And we see that f prime also has a problem with non-existence at 1 or minus 1, because we would get a 0 in the denominator. So f prime also does not exist at x equals minus 1 and x equal 1. So these constitute our critical points for the function. If we plug in x equals 0 to the function f of 0 we see here is 0. So the critical point associated with x equals 0 is the origin. For the other two, they're actually not in the domain of f or f prime, so we can't get y values. And we mentioned earlier, f has the discontinuities at the same points, which means, well, f prime inherits the same discontinuity, and we'll see that we have actually vertical asymptotes at those x values. We also should use our first derivative test, which will tell us where the function is increasing and decreasing, and then we can actually identify if anything is happening at these points in terms of local extrema. I've kind of let the cat out of the bag that these are not going to have local extrema at x equals minus 1 or x equals 1. But we will see that. Let's set up our analysis for the sign of the first derivative. And we could say that f prime is written as the product of minus 2x and 1 over the quantity x squared minus 1 squared. And then we have these critical point, or these critical values of x equals minus 1, 0, and 1. Now, what's interesting is that this term in the denominator term, 1 over quantity x squared minus 1 squared, for the x values where this exists, which exclude minus 1 and 1, which we're not plugging in, this is always positive. So we can actually just go through and label this as always positive. The minus 2x term, if you plug in any x greater than 0, you'll get something negative. So plug in x equals 4. You would get minus 8. If you plug in any x that's negative, you'll get a minus times a minus, which is a plus, and so you'll get something positive. And so we see the sign of this first derivative. Plus times plus is plus, plus times plus is plus, plus times minus is minus, plus times minus is minus. So we see these intervals on which f is increasing and decreasing. So f is increasing where f prime is positive. So we're increasing on minus infinity to minus 1, union minus 1 to 0. So these intervals where the first derivative is positive. And then we're decreasing on the intervals where the first derivative is negative. So f is decreasing on 0, 1, union 1, infinity. Our first derivative test can then be used to identify local extrema. And we see here that as we approach x equals minus 1 from the right, we're increasing. But then on the other side, we're still increasing. So we do not have a local extrema here because the first derivative doesn't change signs. Similarly, at x equals 1, the function is decreasing to the left of 1 and decreasing to the right of 1. So we do not have a local extrema here either. It's only at x equals 0 where the function is increasing on the left of 0 and then decreasing after. So at x equals 0, the critical point 0, 0 is a local maximum. So there are no extrema at x equals 1 or x equals minus 1. So now we've extracted what we need from the first derivative. And now we move on to the second derivative. So for concavity, we need the second derivative information. Here is our first derivative. Let's calculate the second derivative. And so with f prime written this way, we see that this is a product rule question. So f double prime of x we differentiate using product rule. So first, times the derivative of the second, which is a chain rule problem. We have minus 2, leaving the inside alone, x squared minus 1, to the minus 3, times the derivative of the inside, 2x, plus the second, x squared minus 1 to the minus 2, times the derivative of the first, which is minus 2. This becomes, we have a minus 2 times a minus 2 times a 2, so that'll be 8. We have x and x, so we have 8x squared. And then we have the quantity x squared minus 1 cubed in the denominator. For the second term, we have a negative 2 over x squared minus 1 squared. And this will be nicer if we multiply top and bottom of our second term by x squared minus 1. This way, we'll have a common denominator. So if we do this, we have 8x squared over quantity x squared minus 1 cubed. Here we have a negative 2 times x squared, so minus 2x squared. And then a minus 2 times a minus 1, so plus 2. Which reduces to 6x squared plus 2 over quantity x squared minus 1 cubed. And so there we have our second derivative. And remember, with our second derivative, it's a question of what's the sign of it to determine concavity, and things can change sign if f double prime is 0. Now first notice, this numerator is always positive. So the numerator of f double prime is always greater than 0. any x you plug in is squared and multiplied by 6, and then you add something positive to it. So it's the denominator that determines the sign. And by the way, since the numerator of f double prime is greater than 0, this means that the solution to f double prime of x equals 0 does not exist. So we can't find any inflection point via that route. It would only be at a point where the second derivative didn't exist. And again, this also implies that the denominator determines the sign of f double prime. So let's check the sign of that denominator. So we have x squared minus 1 cubed. When is that less than 0? If that's less than 0, then f double prime is less than 0, which will mean the original function f is concave down. So take cube roots of both sides. X squared minus 1 is less than 0. X squared is less than 1. Or x is between minus 1 and 1. This means that f is concave down on the interval minus 1, 1. Similarly, if we check where x squared minus 1 cubed is positive, we have x squared minus 1 greater than 0, x squared bigger than 1, and that happens if x is less than negative 1 or x is bigger than 1. So f is concave up on minus infinity to minus 1 and 1 to infinity. And so notice we found where the function is actually concave down and concave up. But we didn't find any inflection points. That's okay. And I should be maybe more specific. The reason we don't find inflection points is notice that the endpoints of these intervals are all at x equals 1 or minus 1, which is where we have a problem with the function. The function actually has a discontinuity there. So when we graph it, we'll see how this change in continuity actually does occur. So let's now look at the discontinuities. So let's think about what's happening at x equals 1 and x equals minus 1. And remember that we had rewritten our rational function dividing all terms top and bottom by the dominant term of x squared in the bottom. And let's think of what happens at each of these points. So we want to come in a limiting fashion of the original function from both left and right to x equals minus 1 and x equals 1. So what's the limit as x approaches 1, say from the right of f of x? Well, that's the limit as x approaches 1 from the right of 1 over 1 minus 1 over x squared. And let's think about what's actually happening here. 1 over x squared, as x approaches 1 over x, so x squared is approaching 1. So 1 over x squared is approaching 1. But 1, we're approaching 1 from the right. So think like 1.001. 1 over 1.001 squared, which means that this is 1 over something a little bit bigger than 1. So this expression is slightly smaller than 1. So you have 1, let's be explicit here, this is slightly smaller than 1. So in your denominator, you have 1 minus something just a little bit smaller than 1. So you have something very small and very positive. So the denominator is small and positive, which means that this limit will be infinite. Similarly, if we come at this as x approaches 1 from the left of f of x, this is the limit as x approaches 1 from the left of 1 over 1 minus 1 over x squared. But in this case, let's think about that 1 over x squared. We're approaching 1 from the left, so think like 0.999. When we square that, we also have something less than 1. So we're still 0.999 something. So this 1 over x squared term, you have a 1 in the top and a number in the bottom that's a little bit less than 1. So you have a numerator that's bigger than the denominator. But of course, the whole thing is approaching 1. It's just a little bit bigger than 1. So 1 over x squared is slightly larger than 1. So you have in the denominator 1 minus something a little bit bigger than 1. So you have something tiny and negative. Which means, as x is blowing up, this is actually approaching minus infinity. So this tells us that near x equals 1, we have to have the limit as we come from the right. The function is blowing up to positive infinity, and we come from the left, it's going to negative infinity. So we have this kind of vertical asymptote at x equals 1. We can make the same kind of argument now as x goes to minus 1 from the right. And note that things don't change. These two cases will have the same outcome because the only x that appears is x squared. So the fact that we're approaching minus 1 is that's not going to be any different than approaching 1 because the negative 1 is being squared to a 1. So we'll have the same outcome. So as we go to negative 1 from the right, we will also approach infinity. And then as we go to negative 1 from the left, as in this above case, we will have the same outcome of minus infinity. So as we approach minus 1, if we come from the right, we're blowing up to infinity. And if we come from the left, we're blowing down to minus infinity. So this handles the behavior at these discontinuities of f. And we can now bring everything together to see what the graph actually looks like. So let's summarize. We have a local maximum at 0, negative 1. We knew we were increasing from negative infinity to minus 1, and then from minus 1 to 0. And we were decreasing on 0, 1, and 1 to infinity. We're concave up essentially outside of minus 1, 1. Concave down on minus 1, 1. We had this horizontal asymptotic behavior. So as x goes to infinity or negative infinity, f of x was approaching 1. And then we had these vertical asymptotes of x equals minus 1 and x equals 1. So let's put this all together in a graph. and see what this thing actually looks like. So first of all, we saw that we had a local maximum at negative 1, 0. So we know we have this sort of thing. And then we have these asymptotes at y equals plus and minus 1. Excuse me, at x equals plus and minus 1. We also have horizontal asymptotes. So recall we had horizontal asymptotes of y equals minus 1, and y equals 1. Okay, first of all, the function f is increasing from minus infinity to minus 1, and then minus 1 to 0. We have this asymptote. As x goes to minus infinity, we're approaching y equals minus 1. And then remember, as x is approaching minus 1 from the left, it's going to positive infinity. So the graph of our function should look something like this here. We also noted that we were concave up outside of minus 1 to 1. So this is consistent with everything we saw. Again, here we saw the limit as you approach x equals minus 1 from the right was negative infinity. The function is increasing on this interval, and it's concave down. So we can see that our function here should look like this. When we come over here, we know the function is decreasing from minus 1. Sorry, the function is decreasing from 0 to 1. And it's also concave down. So we see this. We know the function is decreasing from 1 to infinity. We know it's concave up. And we know it has a vertical asymptote here and a horizontal asymptote here. And so our function looks like this. And this incorporates all the information that we put together about this function. So we see we have no inflection points. We're changing concavity at these vertical asymptotes, these discontinuities of f, infinite discontinuities of f. And the only critical point, the only relative extremum, was this, negative 1, 0. And there's no absolute maximum, there's no absolute minimum, because the function increases without bound in certain areas and decreases without bound in certain areas. So this brings everything together with an example that moves away from the examples of polynomials. And this is the general approach that you can take now to graph any function that's differentiable. You just have to deal with these troublesome spots where your function might not be continuous, might not be differentiable, or might not be second differentiable. But the principles of using the information in the function itself, the first derivative, the second derivative, and then behavior, limiting behavior, as x goes to plus infinity or minus infinity, or limiting behavior near asymptotes. We use all those tools together to put together a sketch of a graph of a function. So again, this is a very powerful tool. You want to think of this as the real payoff of all the differential calculus that you've studied. You can say a lot about the graph of a function now.